This is going to be our review for exam 5, which is going to cover chapter 9, part of 10, 11, and 15. This is for Chem 110. Now first I'm going to discuss about bonding, non-bonding electron pair, hybridization, electron domain geometry, molecular geometry, and then we'll talk about some of the problems from gas laws. So let me first explain to you what is bonding and non-bonding electron pair with a simple example. NH3. Keep something in mind that would save your time in exam. Whenever you have a nitrogen containing compound, if it's a neutral compound, you'd expect 3 bonds and a pair of electrons. That makes 8 around nitrogen. So anyway, I quickly wrote down this Lewis structure for nitrogen, and this pair of electron is non-bonding electron pair. And these 3 pairs, each of which is holding one hydrogen, nitrogen-hydrogen bond, that's a bonding pair. This is a bonding pair, this is a bonding pair. So there are 3 bonding pairs and 1 non-bonding pair in this molecule. Now why you need to know this? Because total number of electron pairs, I have 4 pairs in this case, that's going to determine hybridization, as well as electron domain geometry. And then finally you stick in these hydrogen atoms to the electron pair, and then you find out the molecular geometry. So from electron domain geometry get molecular geometry. So keep this in mind, that how we come up with hybridization, electron domain geometry, molecular geometry from electron pairs, all the electron pairs around the central atom. So I'm going to explain to you about hybridization first. This is how it goes: S, Px, Py, Pz. Then there will be 5 d orbitals, dz square, dx square, minus y square, dxy, dyz, and then dzx. I just wrote down all these orbitals. Now say I have 2 pairs of electrons on the central atom. Then you need to hybridize. Hybridize means mathematical mixing. Hybridize only these 2, because I need 2 hybrid orbitals to have 2 pairs of electrons. So when I have 4 pairs of electrons, I need 4 hybrid orbitals. Now how do I get those hybrid orbitals? I need to mix 4 orbitals starting from here. 1, 2, 3, 4. So these 4 orbitals, when you mix together, you are going to get 4 hybrid orbitals. So keep that in mind. If you're going to mix 2 orbitals, you're going to get 2 hybrid orbitals. If you're going to mix 3 of them, you're going to get 3 hybrid orbitals. So when I'm mixing S, Px, Py, and Pz, I get the type of orbital, hybrid orbital, is called sp3. sp3 means I combine s and 3 p orbitals, and that would give me 4 hybrid orbitals, because I mixed 4 of them. So 4 hybrid orbitals. So keep this in mind, that depending upon how many pairs of electrons you have, your hybridization would be such that it must be able to house 4 pairs of electrons in this particular case. If I have 3 pairs of electrons, then my hybridization would be S, Px, and Py, or sp2. So keep this in mind. And the other thing I wanted to tell you, that if there are 4 pairs of electrons, or sp3 hybridization, this is going to be the geometry. There will be 4 pairs of electrons at the corner of tetrahedral structure, and this angle is 109.5. It's not 90 degree. It doesn't sit on a plane. It's a three-dimensional structure. So keep that in mind. sp3 hybridization you expect for 4 pairs of electrons, and the angle that we expect to be 109.5 degree. Okay, now that's the normal angle you'd expect. So now this is what you have. Nitrogen with 4 pairs of electrons. Let's assume that hydrogens are not there. If you assume that these hydrogens are not there, only 4 pairs of electrons are there, then this is electron domain geometry, and this is called tetrahedral. You need to know the names of these shapes. It's given in a table in this chapter, so make sure you remember those shapes. Just for example, for 2 pairs of electrons is going to be linear, 3 pairs trigonal planar, 4 pairs tetrahedral, and 5 pairs would be trigonal bipyramidal. So this is going to be tetrahedral electron domain geometry or electron pair geometry. Since you'd have a question on these, hybridization, electron domain geometry, molecular geometry, I'm trying to give you the understanding of how we come up with these hybridizations, angles. Now, stick in 3 hydrogens, because NH3 has 3 hydrogens. Out of these 4 pairs of electrons, you can select any 3. So they're all identical, even though on the board it may not look identical, but they're all identical. They're all like apart from each other by 109.5 degree. So you have 1 pair of electron here, then a hydrogen, let's stick in a hydrogen here. So even though my electron domain geometry is tetrahedral, but molecular geometry doesn't have all the hydrogens bonded here. Like this pair is a non-bonding electron pair. If I take picture of this molecule, this is how it would look like. That means you would have the central atom and 3 other bonded atoms. And this is not tetrahedral because one of the bonds is missing, which has electron pair. So this would not be called tetrahedral, even though electron pair geometry is tetrahedral. This would be, it would look like this if you cover this. So this would be pyramidal. It's a pyramidal structure or trigonal pyramidal structure. Let me write down. Trigonal pyramidal structure. So in this case, we see that electron domain geometry is tetrahedral, but molecular geometry, this is molecular geometry, this is electron domain geometry. Molecular geometry is trigonal pyramidal when one of the end is missing from a tetrahedral structure. If 2 ends are missing, it will be called bent molecular geometry. But electron domain geometry will still be tetrahedral with 4 pairs of electrons. What about the angle between these? They're close to 109.5, but smaller than that. So slightly smaller than 109.5 degree. Now why it is slightly less than 109.5 degree? Scientists have found that whenever you have non-bonding electron pairs like this, they squeeze these bonds. So these bonds are squeezed, and that's why this angle gets smaller than 109.5. So keep this in mind. Whenever there is a non-bonding electron pair sitting, the angle that we expect from hybridization will be slightly smaller because of these squeezing of bond angles by non-bonding electron pair. So in exam, I'm going to ask you a question on electron domain geometry, molecular geometry, angles. So you ought to be ready for that. Now let me give you another example. This example would be for FF4. this is the molecular geometry, a molecular formula SF4, and I'm going to first get valence electrons by looking at periodic table. I'm assuming that you know how to get valence electrons. You look at sulfur and count from left to the right on the same line by looking at periodic table, and you'd find that you'd be counting 6 electrons. So, and those 6 are valence electrons. So 6 valence electrons on sulfur, and then you have fluorine. Again, you count from left to the right until you get F or fluorine, and that has 7 electrons, and you have 4 fluorine. That's 28, and altogether we have 34 valence electrons. Now, you write down S and 4 fluorine. If you follow the rule that I posted in Angel, first draw these bonds and connect it to the central atom by single bond, and then give noble gas configuration to the outer atoms. In case of fluorine, noble gas means 8 electrons. I already have 2 here, then 4, 6, 8. Each line represents a pair of electrons. So 2, 4, 6. So now I have 8 electrons around each fluorine. Now let's count again. 8, 8, 16, 24, 32. So I already assigned 32 out of 34 electrons. So where can I put these extra 2 electrons? You can't put any extra electron on fluorine. If you need to break noble gas configuration, break it for the central atom. So I'll have to put this 5th electron pair on sulfur. So keep this in mind. Outer atoms almost never would break noble gas configuration. So whenever you have too many electrons, place it on the central atom. So the central atom is sulfur. Now, how many electron pairs we have? That will determine electron domain geometry. 1, 2, 3, 4, 5. Altogether we have 5 pairs. So obviously sp3 is not going to do the job because I need to make room for 5 pairs of electrons. So I need 5 hybrid orbitals. So let's start from S. Now I need to include all 5 orbitals. 1, 2, 3, 4, 5. So that has to have 1d orbital. So you're going to write down as dsp3 hybridization, or sometimes in book you'd find sp3d. So that would make 5 hybrid orbitals because you're combining 5 orbitals, 1d, 1s, and 3p you combine together. So that would give you 5 hybrid orbitals. Now you need to know if there are 5 pairs of electrons, what would be the geometry? So I'd like each of you to know these geometries. 1 pair, 2 pair, 3 pair. This is the plane, triangular plane. You have 3 pairs, and then 4th pair on the top, 5th pair on the bottom. So this is the geometry with 5 pairs of electrons. So you have to know these because this gives the minimum repulsion between electron pairs. That's how you can determine these electron pair geometries. So these would have dsp3 hybridization, and the name of the molecular geometry again is in one of the tables is given, so make sure you know this. This is a triangular plane and 1 pair on the top, 1 pair on the bottom. It's called trigonal bipyramidal. So it's a trigonal bipyramidal structure. Now, what are the angles? In the plane, these angles are 120 degree. Outer plane, these are 90 degree. So it's like a triangular plane, and 1 on the top, 1 on the bottom, and that makes 5 pairs of electrons. Hybridization is dsp3. So what angle goes with dsp3? There are 2 sets of angle. One is 120 degree on the plane of triangle. The other one is 90 degree. So keep this in mind. Just a few minutes ago we talked about sp3, which goes with 109.5. dsp3 goes with 120 and 90 degree. Now you have 5 pairs. This is electron domain geometry, trigonal bipyramidal. Now I need to stick in 4 fluorine. Now I have 5 pairs of electrons, so I can select any 4. Normally that's what you'd think. But one of these would be most stable. And I'm going to do write down the most stable one, and after my next example, I'm going to explain to you why this particular one would be most stable. So let me first finish this here as. So this is going to be my molecular geometry, what I'm going to write down. So first, this is trigonal bipyramidal, that's where electron pairs are. Now, you need to attach fluorine, 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 fluorine. This is the most stable way you can organize these 4 fluorine around these 5 electron pairs. And in book, they have a listing of most stable one, and I will show you that how you can predict in case you forget that, because I hate to memorize each and everything. So I'll explain the understanding part later on, even though in book they only briefly mention, but I'll explain to you in details why out of other possibility. What is the other possibility? 3 fluorine could be on the planar base, only 1 fluorine on the top. Now why is not stable? You need to do a little calculation. Actually, that's just a simple understanding of the geometry would help. So this is the most stable arrangement of fluorine, and let me write down this name. This is no longer trigonal bipyramidal. If all these pairs were bonded, say I had another F here, it would be same geometry as this. But when something is missing, when you take the picture of this molecule, it is going to look like this, cover this. So you have a triangular base, and you have 2 fluorine along this direction, and 1 fluorine on the top, 1 fluorine on the bottom, and this is called seesaw. So these names are all given in the book. Seesaw structure. So molecular geometry, so this is molecular geometry. This is electron domain geometry, and this is molecular geometry. And you need to know both for the exam. And hybridization, we already mentioned, is DSP3. And let me give you the next example, and then I'll explain to you about why one particular molecular geometry is more stable than the other possible structures. So let me give you the second example. That way you'll be better prepared for the exam. My next example is XeF2, xenon difluoride. So I have Xe, which has 8 valence electrons. Only you count S and P electrons. If you count from left to the right until you hit xenon, and that would give you 8 electrons. So just P6 and S2, so that makes 8. This is outermost, so you'll be counting along the line where you have xenon. And ignore the D electrons. Okay, now we have fluorine here, the 2 fluorine. Each fluorine has 7 valence electrons times 2, that's 14. Altogether we have 22 valence electrons. Now write down xenon with 2 fluorine. Say I'm just writing down a particular way, F, and then give noble gas configuration to the outer atoms before you even account for how many electrons you placed in. So 8, 8, 16. I already accounted for 16 out of 22 electrons. And I must account for 22. And I don't have any room for adding electrons onto fluorine. So forget about fluorine. So only where you can place these electrons would be on xenon. So let's do that. 16, 18, 20, 22. So that's the kind of Lewis structure that you'd have, where xenon has 2 fluorine and then these electron pairs. So altogether you have now 5 electron pairs. Just like before, this is again going to be, since it's 5, I need to have 5 hybrid orbitals. So I need to mix 5 orbitals. It's going to be S and these 4 orbitals. So we'll call it dsp3 again. Remember this angle to be, there will be 2 sets of angle, 120 degree and 90 degree. So let's redraw that. 1 pair, 2 pair, 3 pairs, 4th pair, 5th pair. So this is going to be electron domain geometry. So electron domain geometry is trigonal by pyramidal. This is electron domain geometry. So during electron domain geometry, just forget about the bonded atoms. Just take their electron, take their valence electrons. And then this is going to be trigonal by pyramidal. Hybridization is dsp3 because you must have 5 orbitals, hybrid orbitals for 5 pairs of electrons. Now I need to stick in only 2 fluorine. Now you have lots of possibilities. I can put fluorine on the triangular base, 1 here and 1 here, or I can put 1 here and 1 here. They're not identical. And I'm going to show you later on, after I give you this, that how we can predict the best molecular formula when you have more than 1 possibilities, like in this case. One pair, 2 pair, 3 pairs, 1 fluorine on the top, 1 fluorine. This is the best structure. Your book, I think it's table 9.2, has given all these best structures. So if you can remember that, that's fine, or I'm going to show you how we can predict the best structure. So this is the best or most stable molecular geometry. This is no longer trigonal by pyramidal. If you take the picture of the molecule, cover these electron pairs. Because in picture of the molecule, electron pairs cannot be seen. Only thing you can see would be xenon with 2 fluorine. So it would be a linear molecule because this angle is 180 degree. So molecular geometry is linear. And that angle is 180 degree. Because this is 90, this is the 90. So the angle between these 2 bonded electron pair is linear. So name of the geometry is linear. So you can see here it's the distinctly different names. What would happen if I had all these electron pairs bonded? Then it would be same as this, trigonal by pyramidal geometry. Now I'm going to show you why this is the best structure when you have 5 pairs of electrons. Best means least of, most stable structure based on all the interactions. Let's assume that you consider another structure for molecular geometry. Say you forgot, because in book they're giving you listing of all these geometries and you probably left to memorize, but in case you forget, you can find out quickly what is the best geometry. So let's write down another possible structures. Okay? Let's make it slightly different. Okay, xenon at the center, and then you have 3 pairs of electrons on the base, 4th and 5th. Okay, let's pick, instead of having 2 fluorine farthest away from each other, let's have 1 fluorine here and the other fluorine here, and rest are electron pairs. Because I don't know at this point which one would be more stable. I just wrote down this, and now you can quickly find out that why this is not as stable as this one. And I'm going to explain that to you on the basis of several interactions. We call this 90 degree lone pair interactions That's the worst kind. It's a destabilizing interaction. So if you have any interaction like this, it will try to break that whole molecule. So this is destabilizing. So 90-degree lone pair is a lot more destabilizing than 90-degree lone pair bond pair, and then 90-degree bond pair. So let me remind you what is this lone pair. These pairs of electrons are lone pairs, or non-bonding electron pairs. And these are the bond pairs between the bonds. Okay, now do I have any 90-degree lone pair here? Yes, this is one of them. And this one is the other one. Let's have a dotted line. So there are two 90-degree lone pair interactions in this molecule. So cross it out. It's a pretty bad kind. So I don't need to calculate the 90-degree lone pair bond pair or bond pair, because as soon as I discover 90-degree lone pair, we can cross out that possibility. Now let's count this one, just out of curiosity, how many lone pair or lone pair bond pair interactions we have. That is 0 90-degree lone pair interaction, because there is no such 90-degree. These are 120 degree. So that's not counted. If it's 120 degree, not counted. It's only 90 degree. Now look at here, lone pair bond pair. This is one of them, lone pair bond pair. Then this is lone pair bond pair, 2, 3 from the bottom, and 1, 2, 3 from the top. So there are 66 90-degree lone pair bond pair, and there is no 90-degree bond pair. So if you come up with even additional structures, you find this would be the best structure based on interactions, because this is the most destabilizing interactions, and so you know that. And since I'll be asking you quite a few questions on molecular shape, electron domain geometry, molecular geometry, make sure you understand these, and that way you can do well in exam. Now let me give you another molecule, and let's see whether it can predict hybridization and angle in that molecule. In my example, this is the third example, I'm selecting HCN. In my previous lecture on exam review, I mentioned to you that if it's a neutral molecule, carbon would have 4 bonds, hydrogen would have 1 bond, nitrogen would have 3 bonds, and oxygen would have 2 bonds and 2 pairs of electrons. Now with HCN, this would save my time, and I'm going to show you how. This is carbon and hydrogen. Then hydrogen would like to have 1 bond, it's already there. And carbon must have 4 bonds, so that means there has to be 3 other bonds, and there's nothing else. So it has to be nitrogen bonded by 3. And that works out. Nitrogen has 3 bonds and a pair of electron. And that's it. This is the Lewis structure for HCN. So this is just to save your time once you get used to writing all these Lewis structures. Now, what is the hybridization of carbon? I now have a triple bond. So keep something in mind. For hybridization purposes, double or triple bond is counted as a single bond or 1 electron pair. It is just for hybridization purposes and angle purposes. You consider double bond or triple bond as a single bond or 1 electron pair. Okay, so now I'm going to count that carbon here has 1 bond or 1 pair of electron, here has another one, 2 pairs. So as if carbon has 2 electron pair, you'd be treating it as carbon having 2 electron pairs. Now, what kind of hybridization? Now, for two electron pair, you need to have combination of two orbitals. So it has to be s and p then. So hybridization is sp. So hybridization is sp. Now we need to know what angle goes with sp hybridization. Let's assume that I have a central atom with two pairs of electrons. This is the central atom, and two pairs of electrons are like this. Knowing the fact electrons repel each other, this is not going to be most stable because they'll be farthest away from each other to be most stable. So this is going to be the most stable electron domain geometry, and that's 180-degree angle, and this is going to be linear. So sp hybridization with two pairs of electrons would have 180-degree angle. So always keep that in mind. In future organic chemistry course also, it's important to know. sp goes with 180, sp2 goes with 120, sp3 goes with 109.5. Okay, so this is going to be 180-degree now. So I can write down this angle is 180-degree. Hybridization is sp. So keep this in mind. My next example would be on polar bond and polar molecule. That would also be on the test. Polar bond and polar molecule. Say the question is SO3, and if we're supposed to find out whether it's a polar molecule or not. And this question is coming from chapter 9, number 43C. First write down the valence electrons. Sulfur 6, oxygen 6 times 3, 18, altogether 24 electrons. Now we have sulfur with 3 oxygen, O, O, O. Give noble gas configuration to the outer atom, and that accounts for 24 electrons. But look at the central atom, doesn't have 8 electrons. So in order to give it 8, bring a pair of electrons in between, so you're going to get a structure like this, S, O, O, double bond O. So this is going to be one of the structures, and there are two other possible structures where you have a double bond here, and third structure double bond here. So I'm assuming that you know about those resonance, so I'm just going to show you the next step. So when you draw the resonance structure, this double bond is going to move from here to here to here. So hybrid structure would have same bond length, which would be 1 1/3. 1.33 is the bond order for this molecule. So now let's focus on the molecular shape. When you have a double bond, this is going to be sp2. Why sp2 double bond will be counted as a single bond? So like 1, 2, 3. So there will be 3 pairs of electrons. So that will be sp2 hybridization or 120-degree angle. Let me repeat this. In one of these structures, you will have to bring this a pair of electron from oxygen onto this. Okay, now that gives 8 electrons around sulfur. But remember, double bond will be counted as a single bond or 1 pair of electrons. So 1, 2, 3. So there are 3 pairs. So I need sp2 hybridization. And sp2 hybridization goes with 120-degree angle. Let me explain to you why these things are easy to understand. Say if I have 3 pairs of electrons, 1 pair here, two pair here, third pair here, they're not going to be that stable because they repel each other. The most stable electron domain geometry with 3 pairs of electrons would be trigonal planar. And that's why in textbook they would say for 3 pairs of electrons, sp2 hybridization, angles are 120 degree, and this is trigonal planar. So this is going to be trigonal planar geometry, sp2 hybridization. So when, in case of SO3, you would have oxygen like this, and so molecular geometry is same as electron domain geometry, so it'd be trigonal planar because all these electron pairs are bonded. Now, our original question was whether it's a polar bond or polar molecule. Let's now focus on this. I had to do all these just to give you the background and understanding. If you look at periodic table, oxygen is on the top of sulfur, so it's more electronegative. Oxygen is more electronegative, so it's the delta minus. This is more positive. So there is a electron pull from sulfur towards oxygen. We can call it dipole force or dipole moment. Similarly, we have another force coming from here to here, another one coming from here to here. This is very symmetrical. Trigonal planar, 120 degree apart. So these 3 forces cancel out. If they cancel out, this is going to be nonpolar. So in a nonpolar molecule, you'd expect highly symmetrical structure, and all these forces in highly symmetrical structure would cancel out, especially if when each kind is made up of same element. So in this case, oxygen, oxygen, oxygen. So overall molecule is nonpolar, but each bond is a polar bond because there is an electronegativity difference between sulfur and oxygen, oxygen being more electronegative. So nonpolar molecule, but each bond, each SO bond is a polar bond because of electronegativity difference. So make sure you understand the difference between polar bond and nonpolar bond, polar molecule and nonpolar molecule. The next type of question I'll go over is on sigma and pi bonds. So in exam I'd be asking you how many sigma bonds are there, how many pi bonds are there in a particular compound. So sigma and pi bonds. Say I'm looking at a number of compounds. One of them is C2H6, C2H4, C2H2. I'm not going to do all of them, but I can show you at least some of these. This is an organic compound. Remember, carbon would have 4 bonds. With that in mind, I can quickly write down H, H, H. So this is a structure for C2H6. Each carbon has 4 bonds. And question is how many sigmas we have here. Each of these is made up of sigma bonds because hybridization is sp3. Remember sp3, 4 pairs of electrons, so we need sp3 hybridization for 4 pairs of electrons. So each of these carbon has sp3 hybridization. And if you look at periodic table, all the valence electrons, carbon has orbitals s, px, py, and pz with electrons. So when you use sp3, you use up all the p orbitals. So these will be all sigma bonds. This is also sp3, this is also sp3. So all sigma bonds. Just to remind you, sigma bonds are formed by the head-on overlap, and pi bonds are formed by lateral overlap of orbitals. In my lecture note, we gave you pictures of these, and book also has those pictures. So they're all sigma bonds. Let's count how many. 1, 2, 3, 4, 5, 6, 7. So there are 7 sigma bonds. They are formed by head-on overlap. And I'm going to show you one of these between carbon and carbon so that you understand. Remember, each carbon has sp3 hybrid orbitals, so that means there are 4 hybrid orbitals. It's going to look like this, and other carbon also would have something like this. So this is a sigma bond between carbon. Similarly, there's a sigma bond between other hydrogens. One would be like this. This is 2, then this 3, this is 4. This will be all like 109.5 degree. This is for hydrogen. This is for hydrogen. This is for hydrogen. Same thing happens on the other side. I'm just showing you how they look like. These are all formed by head-on overlap. So this is about C2H6. Now let's try C2H4. Carbon, carbon, and then I distribute those hydrogens between these two carbon. Hydrogen, 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 hydrogen. That makes C2H4, but carbon doesn't have 4 bonds. Only way I can make it 4 bonds would be by making a double bond here. So this would save my time. I quickly write down this. Now, hybridization, remember double bond would be counted as a single bond. 1, 2, 3. 3 pairs means I need to combine only 3 orbitals. So it would be sp2. And you remember that sp2 goes with 120 degree angle. So this is going to be 120 degree. sp2 hybridization. Now keep in mind, when I have sp2, originally we had this px, py, pz on carbon at the same energy, so obviously it's empty. We can promote an electron. Actually, that's what happens during bond formation. One electron goes in there, and then finally they overlap. So that, in short, we can say that sp2 hybridization used for sigma bonds, and for pi bonds, the pz orbital is being used. So how many sigma bonds? 1, 2, and one of these 2 bonds. 3, 4, 5. So 5 sigma, and between these double bonds, one is a sigma, the other one is pi, which is formed by lateral overlap. So 5 sigma and 1 pi. Let's quickly write down C2H2, which would have a double bond, and carbon has 4 bonds. And again, 3 bonds to be counted as 1 bond and 1 pair, so that 2 pairs. sp is the hybridization. Angle is 180 degree. sp goes with 180 degree. And obviously we have py and pz for making, so sp would be used for hybridization. And that goes with 180 degree. py and pz would be available for pi bond formation. So py of one carbon overlaps with py of the other carbon. pz of one carbon overlaps with pz of other carbon, giving those 2 pi bonds. Okay, now, so there are sigma bonds because of sp, so let's highlight those. One of these is sigma, one of these is sigma. In Lewis structure, they don't distinguish sigma and pi bonds, but you have to know from this analysis. Again, this carbon would also have this sigma, so it would be 1, 2, 3. So 3 sigma bonds, and these 2 are pi bonds. 2 pi bonds. So make sure you know how to get sigma and pi bonds. Next, we'll talk about gas laws. I think this is the 7th problem. I kind of lost track of this number. PV equals to nRT. Pressure, volume, moles, R is a constant, 0.0821 liter atmosphere per degree Kelvin per mole, temperature in Kelvin. So if you're going to use it, keep those in mind. Also, in some problems, you need to use this, P1 V1 over T1 equals to P2 V2 over T2. The only thing you need to know that this temperature will have to be in Kelvin. But pressure could be any unit, but you have to be consistent with your choice of unit. If this is a millimeter of mercury, it has to be millimeter of mercury. If this is ml, this is also going to be ml. On the other hand, for this one, since this value has 0.0821 liter atmosphere Kelvin mole, if you're going to use this, your temperature has to be in Kelvin. So temperature has to be Kelvin in both types of solutions, equations, but this is number of moles, but pressure has to be in atmosphere if you're going to use this. And volume has to be in liter. That way we'd be all consistent with the units. Next, in exam, there'll be a question on density calculation at STP. So let me write down that. Density at STP. STP stands for standard temperature and pressure. So standard temperature is room temperature, like 25 degrees centigrade or 298 Kelvin. And you have pressure is 1 atmospheric pressure. So if that's the case, 1 mole of a gas occupies any gas 22.4 liter. So you can say at STP 22.4 liter per mole. Now, what is the density unit? Density unit is gram per liter, if I want to write down a liter. So I can use dimensional analysis method to get the density when it's the STP is given. Say for example, molecular weight is given. Say molecular weight of a gas from the formula, or if it's just number is given, say it's 44.8. I'm just making this number 44.8. Since this is molecular weight, you have a gram on the top, mole on the bottom, or molar mass. It's the same thing. So now we can write down density would be given by 44.8 gram per mole. Remember, I must have gram on the top and liter on the bottom to get density. So I can use this. Now, if I use additives, where liter would be on the top, mole would be on the bottom, it's not going to work out. So I need to flip it so that mole goes to the top. So mole goes to the top, liter on the bottom, so this 22.4 goes with the liter. So keep that in mind. Mole would cancel out, so that gives me 2.00 gram per liter. And there would be a question like this in exam. So it would be simple, this is a simple example, and you can come up with additional problems for practice. You can also use this formula, D equals to PM over RT. Because if the condition is not STP, then obviously you have to use this expression. P for pressure, M for molecular weight, R, we already know the value, which is 0.0821 T's temperature in Kelvin. The next problem is Graham's law of fusion. basically, this is what Graham's law, in case you forgot. It's a good idea to first know the theory. Say I have a mixture of two gases. One is the lighter gas, the other one is heavier gas. So that's bigger. Bigger ones are heavier, and lighter ones are smaller. And I made a small hole in here. But what you'd find out, the lighter ones, which is moving faster, would come out of this hole much faster than the bigger ones. And our common sense would say so, because lighter ones would be moving at random much faster, so there's a greater chance it would come along this path and come out. But Graham's time, it was not, all these were not that obvious. So there'd be a question on the application of Graham's law of diffusion, where I'd give you two gases, and based on that, you need to calculate either molecular weight or the rate. Now, one of the examples that I picked from the book, which is chapter 10, number 92. So basically, by reading that question, I find out the following. 105 second for 1 liter of gas, let's call it X. Gas X takes 105 seconds to come out of that box. So 1 liter, for every 1 liter, you have to wait for 105 seconds. The second gas, which is a known gas, for oxygen, for example, it takes only 31 seconds. So the gas is O2. So if that is the case, what is the molecular weight of X? So from Graham's law of diffusion, you can find out molecular weight of this unknown gas. Now how can I do that? Let's first calculate rate. Rate in first case, 1 liter gas of unknown gas is taking 105 seconds. So liter per second is going to be the rate. So it'll be 1 over 105. So rate X, let's call it rate X. For the second one, it will be the rate O2. Again, 1 liter of that oxygen gas takes 31 seconds divided by 31. So obviously oxygen is slower compared to the other molecule. It has to be heavier than oxygen, for which it's taking much longer. So rate of oxygen, I tend to write down the faster one on the top. That way I get larger than 1 as my final answer for the ratio. Rate X will be given by 1 liter by 31 seconds divided by 1 liter by 105 seconds. Now, here we're going to apply Graham's law of diffusion, which is inversely proportional to square root of molecular weight. Now, rate of X was on the bottom, its molecular weight would be on the top. So molecular weight of X on the top, and oxygen was on the top, so its molecular weight would be on the bottom. That's coming from Graham's law. Okay, so now we're going to write down this 105 on the top. If you do the algebra, 105 on the top, and then 31 on the bottom, equals to square root of mx over 32. If you solve it for mx, this is what we get. 367.1. So that's going to be molecular weight. If you write down in unit, that's gram per mole. So the unknown gas has the molecular weight of 367. As you can see, oxygen O2 is 32, so it's a lot heavier than oxygen. And that's what is expected, because it's taking much longer to come out of that box. And there'd be a question like this in exam. The next type of question would be on manometer. is going to be 10th problem. This is on manometer, and there'll be a question on this manometer. These are all straightforward problems, and I'm picking this problem, chapter 10, number 25 from the book. So basically you have a gas sample. This is the manometer. This is for your understanding. I'm drawing this. So it's gone down in here and it's gone up here. This is all liquid. Normally mercury is used, and in this case mercury, they're using mercury. This is 67 centimeter. This is called open-end manometer. This is the gas here. So you have a gas sample here. It presses this column of mercury down here, and that goes up here. So there's a height difference of 67 centimeter. And outside pressure, this is open to the atmosphere. That's why it's called open-end, is 0.995 atmosphere. 0.995 atmosphere. So the question is, what is the pressure of the gas? So make sure you know open-end manometer, closed-end manometer. Closed-end manometer, this end will be closed. So there is no atmospheric pressure. It will be vacuum in that case. Now how does it work? Let me show you here. I often give simple analogy of seesaw. Like as if this is the seesaw horizontal line. Whenever it's horizontal, pressure on this end is equal to pressure on this end. So what do I have on the left-hand side? Pressure of the gas equals to, on the right side, 67 height of the mercury. And let's change it to millimeter, because millimeter of mercury would give me torr. So multiply that by 10. So 670. This is same as 670 millimeter of mercury. So this is millimeter of mercury. Plus, I have this pressure. So that's going to be 0.995 atmosphere. That has to be changed in millimeter of mercury. So 0.995 millimeter of mercury. Now, depending upon the question, if the question is asking everything to be calculated in atmosphere, you need to change it to atmosphere. So let me, I think in this particular problem they're asking for final answer in atmosphere. So if that is the case, you have to divide by 760, 670 divided by 760 atmosphere. So this is going to be 670 divided by 760 atmosphere. And 0.995, I don't need to change it if this question is asking for atmospheric pressure. I just wanted to remind you 760 millimeter of mercury makes 1 atmosphere. So if I do this final calculation, it's going to give me 1.88 atmosphere. Does it make sense? Always it's a good idea to do this kind of checking, whether answer you got, whether it makes sense or not. Yes, because mercury level, when there is no gas, it would be the same on both sides. Since it had gone down this way, that means this pressure has to be exceeding 0.995, and that's what you're getting. And it's exceeding by 670 millimeter of mercury. That's another way of doing this calculation. My next problem, again, there'll be only part of those sections we are going to cover for this exam. Next one will be phase diagram. You just need to know what phase diagram is and understand different part of phase diagram. So this is on phase diagram. Typical phase diagram looks like this: pressure along y-axis, temperature along x-axis. Then it's going to look like this. Book has